Question 4. Substances P and Q react in a solution at constant temperature. The initial rate of the reaction was studied in 3 experiments by measuring the change in concentration of P over the first 5 seconds of the reaction. The data is in Table 1. So let's have a look at P. 0 seconds, then 5 seconds later the concentration has changed. And in experiment 2, 5 seconds later the concentration has changed. 5 seconds later the concentration has changed. The concentration is coming down because P is reacting. Show the initial rate of P for each experiment. So what you do is rate is the change in concentration divided by time. So work out the change in concentration, 1 times 10 to the minus 2, take away 0.92 times 10 to the minus 2, which is 0.08. Times 10 to the minus 2, and then divide by 5, and it comes out as 1.6. I do the same for experiment 2. Take these two numbers away, 0.16 times 10 to the minus 2, divided by the time, 5 seconds, and it'll come out as 3.2 times 10 to the minus 4, and then the same here, 0.5, take away 0.34 times 10 to the minus 2 is 0.16 times 10 to the minus 2, divided by 5 is again 3.2 times 10 to the minus 4. Now what I've got to do is I've got to determine the order with respect to P and the order with respect to Q. So what I'll do is I'm going to ignore the 5 seconds now. I'm just going for the initial rate at 0. So I'm going to ignore the 5 second rows, and I'm going to look between experiment 1 and 2 and see if either P or Q hasn't changed. Yes, Q hasn't changed. 1.25 times 10 to the minus 2 is the initial concentration for experiment 1, and it's the same for experiment 2. So I'm going to take an extract of those two. This is the concentrations of P between experiments 1 and 2, and this is the concentration of Q between experiments 1 and 2, and I've taken the rates for experiments 1 and 2 here. Experiment 1, 1.6 times 10 to the minus 4, experiment 2, 3.2 times 10 to the minus 4. So I've got these here, and what I then do is I take this one and divide by this one, and raise it to the power x. X is the order with respect to this chemical, which is P. Then I do this one divided by this one, and raise it to the power y. Y is the order with respect to Q, and I divide the two rates. I don't raise those to any powers at all. Then this is 0.5 to the power x, where x again is the order with respect to P. These two cancel, that's why I've chosen two numbers that are the same. So that cancels, so this whole section cancels out. So 0.5 to the x equals, these two come out as 0.5. X, the order with respect to P, can only ever be 0, 1 or 2. If it's a 0, something to the power 0 is 1, so it's not a 0. If something is to the power 1, it's itself, which it is, so x is 1. If it's different, then it must be a 2. And x can only ever be a 0, 1 or a 2. So x is 1. Now I've taken experiments 2 and 3, and I've taken P, the initial concentrations of P in experiment 2 and 3, the initial concentrations of Q in experiments 2 and 3, and I've taken the two rates between experiments 2 and 3, which happen to be the same. I'm going to do the same thing again here. 2 divided by 0.5 times 10 to the minus 2. I know that the order with respect to P is now a 1, so x is a 1. I don't know why, that's what I'm going to try and find out. 1.25 times 10 to the minus 2, 2.50 times 10 to the minus 2 to the power y, well y is with the order with respect to Q, and I've got these two which happen to be the same, so that's going to be a 1. So 4 to the power 1 for this one equals 0.5 to the power y. These two numbers are the same, so it equals 1. 4 to the power 1 is 4. Take this across to the other side, so 1 divided by 4 turns out to be 0.25, so 0.5 to the y equals 0.25. Is it a 0? No, because if y was a 0, then this number here would be a 1. Is it a 1? No, it's not, because 0.5 to the power 1 would be 0.5, and it's not. Therefore, y must be a 2. And you can check that. 0.5 squared is 0.25. So order with respect to Q is a 2. Question 4.3. A reaction between substances R and S was second order with respect to R and second order with respect to S. So I can write that here as rate equals K r to the 2, s to the 2, the concentration of r raised to the power 2, s to the power 2, because the initial order with respect to r is a 2, second order, so that's a 2. Order with respect to s is a 2, so that's a 2. Then what's it tell me? It tells me the initial rate was 1.2 times 10 to the minus 3, so that's the rate, equals k. I don't know that, that's what I've got to try and find out. It's given me the concentration of, the initial concentration of r was 1.00 times 10 to the minus 2. I'll put that in. That needs squaring because there's a square here. And 2.45 times 10 to the minus 2 was the concentration of S. Again, that needs raising to the power 2. It needs squaring because there's a 2 here. It's order with respect to. So I've just multiplied these out now. 1.2 times 10 to the minus 3 is K, multiplied by 6 times 10 to the minus 8 is this here. Divide both sides by 6 times 10 to the minus 8. K is 1.2 times 10 to the minus 3, divided by 6 times 10 to the minus 8. 2.00 times 10 to the minus 4. Everything's to 3 significant figures, so I've put this value 2.00 times 10 to the minus 4. Now I need the units. So, units. Rate. Rate is always measured in moles divided by decimeter cubed and seconds. Equals K. I don't know the units of K, that's what I'm going to try and find out. A concentration is moles divided by decimeter cubed. So I've got moles divided by decimeter cubed multiplied by moles divided by decimeter cubed because it's squared, multiplied by moles divided by decimeter cubed multiplied by moles divided by decimeter cubed because it's squared. So I've got 4 moles divided by 4 decimeter cubed. I'm going to cancel a mole on each side. I'm going to cancel a divide by a decimeter cubed on each side. So now my units are 1 because that mole's disappeared. The decimeter cubes disappeared, divided by S, and I've got 3 moles on the right, divided by 3 decimeter cubed. I'm going to take the decimeter cube from the bottom on this side across to the top. I'm going to take the 3 moles on the top here down to the bottom. So K is decimeter cubed, decimeter cubed, divided by mole, divided by S. The S is still on the bottom. So that's, add these 3 3's here to make a 9. Mole is mole 3, but because it's on the bottom, if I'm bringing it up into standard form onto the top, it's mole to the minus 3. S is to the power 1. On the bottom, it's a 1, but on the top, in standard form, it's S to the minus 1.